Hello. Now we will discuss some machine learning fundamentals, right? Again, we are making some imports, right? Here also we'll be using this decision tree classifier. So what would be the learning outcome from this lecture? We'll see how the decision boundary changes with the max depth hyperparameter. We'll see the concept of generalization. That means we'll discuss about what is the generalized model. After that, we'll split the data into the training and testing part using train test split functions. We'll explain the difference between train validation test and the deployment data. We'll also see the difference between training error, validation error, and the test error. We'll use the cross validations. We'll understand what the cross validation is, and then we'll use this cross validation technique using cross val score function and cross validate functions, right? And we'll also recognize what is the underfitting and overfitting, right? Like we'll discuss that, like which model to choose based on this underfitting and overfitting techniques, right? We'll see why it is generally not possible to get a perfect test scores on a supervised machine learning problem. We'll also describe the fundamental trade-off between training score and the train test gap. We'll see the golden rule. What is the golden rule in this machine learning this field we have? And then we'll start build a standard recipe for supervised machine learning task, right? So we have a lot to discuss in this lecture. So first we'll discuss about the generalization concept, right? So in machine learning, what we want is we want to learn some functions, right, which makes the relationship between label data, right, and from which makes the relationship between x and the y, right? So we learn the mapping function from the label data, right, that we can predict on the unlabeled data. That means in the training data we have the x and the y part, right? We want to make a function that relate x to y, but now we want to use that function to predict the y for the x value. That means we have the test data where, or we have the data where the y part is not available, so we want to predict the outcome of that. For example, suppose we want to build the spam filtering systems. So what we'll do is we'll take the large number of spam and non-spam messages from the past data, and then we'll learn the pattern which uh, like relate the spam and non-spam messages. And then after that, after we learn the pattern, whenever I'm saying this learning the pattern, this means that we want to build the model. After that, we want to predict whether this new incoming message is spam and non-spam based on those patterns. So we want to learn from the past, but ultimately we want to apply that knowledge to the future data, right? That is what a generalized model will do. So the question is how we can generalize from what we have seen to what we have not seen. That means we have seen the training data, right? And we want to learn the model using the training data, and those training data was our past data. And now we want to use that model, that the same function to kind of predict on the future data. So in this lecture, in this file, we'll see how to tackle these problems, right? Now let's discuss, before that, let's discuss this model complexity and the training error. In the last lecture, we have already discussed about the what is the decision boundary and how we can visualize the decision boundary. Again, this visualizing of this decision boundary is just for this lecture only, right? So you won't be kind of create a different diagram to kind of visualize it, because in the real world we have a lot of dimension and that is not possible to be visualized, right? But here we want to classify the example as in positive and the negatives, right? So let's examine how does a decision boundary changes with the different tree depth. So again, remember that tree depth was the hyperparameters. So here we are reading our data. This is our the same data we had. The y value is a plus and not a plus, which is the value of quiz 2. We are separating x and the y. Here we have taken the subset of the training data. So we have only chose the two column, lab 4 and the quiz 1, right? Now here we have set this hyperparameter as depth as 1. we have initialized this machine learning model. We are applying the fit model, and then we are doing the scores. Now when we here, so this score value will give you the accuracy, but here we want to predict, or we want to print the error. So we are saying this 1 minus score, that will be the error, and then we are predicting. And like here we are kind of plotting our decision boundary and the tree itself. Here we can see that, so the error we have as in 28% with the max depth 1. And this is the simple example. So here this model has taken decision based on the lab 4, because with the depth 1 we can only build these tree only, right? So we have taken the decision based on the lab 4, right? And here we can see that. Now here we have chosen the depth as 2, again the same code. Now with the depth 2, now our error has reduced. Earlier our error was 28%, but now our error is 19%. So as we are increasing the depth of the tree, right? So error is being reduced, and here we can see that, right? This is the tree. We can see the first decision was taken based on the lab 4, then we have taken decision based on the quiz 1, right? And here we can see the boundary for lab 4 and the quiz 1. Of course this boundary is not visible, but again we can see that, right? So here you can kind of build a straight line, and then you can see that beyond this is a different class and above is the different class, right? This is how the decision tree boundary build we make, right? Now here let's look at the decision boundary with depth as 4. Again the same code. Here we have created a decision boundary with depth 4, and now we can see that here even for the tree itself has become complicated, so as the decision boundary has become. Here we can see that for this one example as well, right? We have built a decision boundary. For these two example we have built a different decision boundary. So what is the meaning? So the meaning is, when the model becomes, if the model becomes more complex, that means it will make a decision boundary even for a single example. Like over here we can see that it has created this decision boundary for just to classify this example as a correct example, right? And here as well you can see that it has created a simple this straight complex decision boundary just to classify these two examples correctly, right? So as the parameter changes, so the model uh so our this model complexity also changes, right? Here let's see again, you can also check the error. We have this as 4%. So as you are, so with the depth 4 your model has become more complex, right? So as the model complexity increases, right, the score on the training data, again every time we are training the model on the training data, and then we are checking the score on the same data, right? So we are checking the error is being reduced after the model is being complex. Here let's make the more complex model. Here we are saying depth at 6. So again we want to we want to grow a more complex tree, and here we can see that with the depth 6, right? What is the accuracy? So what is the error we have? We have the 0 error. That means we have built the 100% correct models, right? And here you can see that to classify these examples, right, it has created this complex kind of boundary, right? And here we can see that now we have this more complex tree, right? So what we're seeing over here is, as the model increases, as the model complexity increases, right? So the training error is being reduced, right? Now what we're trying over here is, here we are just trying to take a different depth value. So we are trying this depth value from 1 to 18, right? And then we are building a model here in this code, right? We are building a model, right, with a different depth and checking the score on that. After fitting it, we are checking the score on a different depth. After we check the score, now we can calculate the error, and then we are checking, here we are calculating and storing the error with a different depth parameter, right? And here we can see the, and also plotting it. Here we can see that with the depth value 1, our error was approximately 28%. With the depth value 2, our error has been reduced to 18%, right? With the depth value 3, our error has been reduced to 0.4%. With the depth value 6, our error has been reduced to 0%, right? And after that, here we can see that now there is no change, no improvement, because there is no example to be classified as a perfect like there is no example which needs to be classified, right? All the example has been classified perfectly. right? So here we can see that our model has shown a 0% error with depth greater than equal to 6, right? But again, as we are growing more and more complex model, our model is being complex, and it is being more specific, more sensitive to the training data. How? We can see that here, to classify just one example, it has built a different rule. To classify this example, again, this is just the one example, it has built a different rule. So now our model is trying to classify each examples correctly, right? It is building rules, it is making rules to kind of justify even for the one examples, right? So here we can see that now our model is being more more kind of tent it is more sensitive to the training data now, right? So the question is it good or bad? Again, here we can check the accuracy. So again, we can see that the accuracy is being increasing as the max depth is increasing. That means max depth is the hyperparameter. So if the max depth value is low, our model is less complex. If the max depth value is high, our model is more complex, right? Here we can see that as we increase this max depth value, our model complexity increases, so our accuracy also increases, and this is on the training data. So at this point, we want to ask, or we should ask, how to pick the best depth value. So how can we make sure that the model we built will do well on the test data as well, or on the deploy data as well, right? Here we are testing our model on the training data, but now we want to make sure that now our model will work perfect on the test data as well, right? Then only it will be useful, otherwise it is not useful. We do not want to use that model, or will not use that model in the real world, right, on the training data. We want to use that model on the test data or on the deployed data, right? So here comes the generalization fundamental goals, right? So now next we'll learn about what is the basics fundamental goal of machine learning. Hello. Now we'll discuss about some fundamental goals of ML. So basically what we want is, we want to build a model which will generalize on all the data, right? So basically we want to build a model which will generalize beyond the training example, right? And the problem is we only have the limited access to the training data, right? And we want to learn this mapping function that will predict the target value, right, as well as the training data, right? That is what our fundamental goal is. Again, consider that as an example, consider that we have this training data, right? So we have used these training data, so the emoticons used for the cat and the dog, right? And here we have this new examples. So again, consider that if I build a model using this training data which has learned about the emoticons for the cat and the dog, but let's say that now we want to predict the y value for these emoticons. So again, for this, we know that this is a cat, this is a cat, this is a cat. But what about this? What about the strawberry? So again, remember that our model only know to say dog and cat, right? It has not learned anything. So either it will say cat or either it will say dog. So if it is not cat, maybe it will say it's dog. It will not say that it's an unknown entry or something like that, but it will speak either cat and the dog. So that's the how machine learning work, right? So we have to be careful that what type of training or what type of training data we are passing and what type of testing data we have to passing, right? We have to be kind of very much uh, it's like we have to be kind of very much reserved for the test data, right? So that is how the machine learning works, right? Now let's talk about the training error and the generalization error. So consider that we have this model M in the, and the people in in the machine learning, the people usually talk the two type of error in the in the machine learning models, right? So the first error is error on the training data, and the second error is error on the entire distribution of the data. What do I mean by error on the entire distribution of the data? So consider that if you are taking the data for the training, right? Now that data has to follow some data distributions. We know this from the statistics, right? Any data, or any data has to have coming from the some distribution of the data, right? So basically, here is an interesting thing is, right, we want to train the model on using the training data, right? But we want to do as well as on the on their distribution of the data, right? So we do not have the entirely access to the data distributions, but we have the some part of the data. So if we know, so the theory is, if we know the exact training data, so we can also know the data distribution. So if we build a model using the training data, and let's say that our model is working 90%, right? So our that model will also work the same way, like it will also give you 90% accurate on the other data which is coming from the same data distributions, right? That is what the generalization accuracy or the generalization error is, right? Now for that, now again, the question is, how do we test it? How do we test that whether this model will work too well on the generalized data? For that, we know that we do not have the access to the entire data distribution. So what we'll do is, we'll do the data splitting. So first, we'll kind of check the, like here, we'll kind of approximate the generalization error. So how do we approximate the generalization error? So the common way is data splitting. That means we'll split our data into a two portions. Let's say that the first portion is the training data and the second portion is the test data. So we'll train the model on the training data, right? And then we'll check the score on the training data. Like we'll kind of check the accuracy of the trained model on the training data, right? And then we check that, okay, now our model is accurate, 90% accurate on the training data. Now what we'll do is, now the test data which was selected from the same training example, right? The same data we had earlier, but now, so the question is, if this model is working 90% accurate, if this model is 90% accurate on the training data, so this model should also work as good as the training data on the test data as well, right? That is how we'll approximate the generalization error. And here we'll think that this test data is coming from their data distributions, or it is coming from their real data distributions, right? That is how we'll approximate the generalization error, right? So here, how do we split it? We can do the simple splitting. We can split the data into the 80 and the 20% of the ratio, right? Consider that we have this toy example over here. We have this toy example which have this total 10 examples. We have the feature and the target value. So we'll use this trend test split function from the scikit-learn. Again, we'll see how to do that. But here we'll split into two parts: training, like train split on the test split. The first part will be called as a train split. The second part will be called as test split. Now, what is the what is the difference between both? So the training split can have the larger portion of the data, and the test split will have the smaller portion of the data. So that here we'll say that, if again we already know that machine learning do well on the data set, like if we have the large amount of the data set, machine learning tends to do well. So we'll kind of, we want to keep the training data like large, right? So that our model gets trained properly, and then we want to test that model on the test data. Again, here in the during the splitting, we also want to do the random splitting, right? So we do not want to just kind of split like first 8 is the training data, and then the next two example is the test data. No, we'll not do that. We'll randomly shuffle the data and then we'll split it, right? That is how the train test split work, right? Here is an example for that. Consider that we have read the data. This is our Canada US city data sets, right? So we have read this longitude and the latitude. right? This is our y value. Now we need to import train test split functions from the model selections, right? So here we are importing train test split function. In the train test split function, we are passing x and the y, right? And then which will return you the two part of the x and the two part of the y. Now here we are also specifying this test size as 20. That means we are saying that we want the test size as a 20% of the data, right? So here when you pass x, it will split into two part, x train and the x test. When you pass y, it will split into two part, y train and the y test, right? So it will split both x and the y variable into two part, training and the testing, right? And here we can check the shape of the entire data and the training and the testing data. Here we can see that. So our original x data was 209. So now the training portion of the data is 167 and the test portion of the data is 42, right? Here we can see this like test data is the 20% of the entire data set, right? We can also create something like that, like instead of splitting x and the y, we can also do something like instead of separating x and y and then do the splitting, we can also do like we can directly pass this entire data frame and then we can split this training portion and the test portion. So again, when we pass this, whatever the data frame you will pass, right? So it will split into two part, training and the testing, right? Again, this would be useful if you want to do the data explorations or if you want to visualize the data, right? So in that point, this will be useful. And after that, after this, now you can split into x and the y portion of the data, right? Now here is the here we can see this entire data we are plotting over here in this graph. Here we can see that these are Canada USA data set, right? And we are plotting entire data over here. And here after that, after we plot it, now what we're doing is now we are using this decision tree classifier. We are fitting the model on the training portion of the data. What do I mean by fit? Again, we have discussed about that. So fitting the model means learning the model. Here we are learning the model on the training portion of the data, and then we are applying the plot over here. Here we can see that this is our plot we can see on the training data. Now our model is very much complex. Now this complexity we are getting because we are not controlling the decision tree. Now by default this decision tree will grow as long as if not all the leaves are the pure leaves, right? So again, it will grow if any of the leaves are not pure, it will kind of try to make it as a pure leaves, right? By segregating the data into the two portions, right? And that's the reason we have seen that it's a full grown decision tree. And this is called full grown decision tree. So now here we can check the score on the test data. And now we are using the same score on the, so here we have used the score on the trained data and then we are checking the score on the test data, right? Again, if you already have the test data, right, you do not need to retrain the model on the test data. Why? Because model has already been seen the training data. Now we just consider that this test data is something like which is coming uh, data from the from that training data distributions, right? And the important thing here, we can see that our training score is the 100% and our test score is 72%. Now, the gap between accuracy of the training and the testing is very large, right? And this again will kind of discuss why is this happening, right? And here we can see the decision boundary plotting. We can see that these are decision boundary plotting, right? And this is our entire training data set we have, right? This is our entire decision tree, right? Built on the training data set, right? Now here what we are doing is, so here we have passed this entire data. Here we have passed the model and the entire data, but here we can see that now we are plotting the two plot, right? This is the plot on the training data set and this is the plot on the tested data set. We can see that this is the decision boundary built using the training data set and this is the decision boundary built on the tested data set, right? So again, to split the data into the train test split, we can see that. So we have this multiple argument like the trace, like the test size we can specify. We have already seen that we have passed the test size as 0.2, that is 20%. We can specify train size, we can specify the random state, all this argument we can specify, right? Now, what is random state? So again, this random state is something that is an basically it will like it's an argument to kind of control the shuffle of the data, right? If you specify the random state, like over here we had specified the random state as 1 2 3. So every time when you shuffle the data, it will be in the same shuffle format, right? So again, it's again the randomness, but the randomness in the controlled environment, right? But but here sometimes people often split the data into the three portion: training, validation, and the test split. So what is the validation data, right? So over here, validation data is similar to the test data as well. Like over here, we had this entire data set X and the Y. We have split the data into the two-part train and the test. And then the validation is something which has been splitted from the test, which has been splitted from the train data as well, right? So what do we do essentially is, right? So like this is how we kind of split the data into the three part: training split, validation split, and the test split. So what we'll do to the validation data? So validation data will be used to test the model. So what we do is, let's say that if you build the model, right, and then if you want to test it, so for testing we can use the validation data, right? But after you are satisfied that this model can works great, this model is the best model based on the validation data, and then we'll check once with the test data. That is how the format we do, right? So like here, the training data will be used to train the model, and the validation data will be used to set or tune the model. So when I'm saying the tuning the model, that means we want to make a model which can works as great as on both training and the validation data. Let's say that if your model is working 95% on the training data, that should also work 95% on the validation data. If you do not achieve it, we'll kind of change the model, right? So changing the model means we'll kind of tune the model or use a different algorithms, right? So here we'll use this validation data to kind of make our model very much similar to that, like make our model as great as kind of training data, right? And this training data model, or like this model, should also work or give the same performance to the test data, right? We want to use this validation data for that. So here, after that, after we are satisfied with the model, now we'll use the test data to check at the last time whether this model is kind of will do well on the deployment time or not, right? That is how we use the test data, right? So what is deployment data, right? We have often seen this the other data as well, like deployment data. So now we have the training data, validation data, test data, and the deployment data. So here you can see that, right? So we use the training data to learn the model, to check the accuracy, and like to kind of check the model performance. We'll use the validation data. So we'll not use the validation data to train the model. We'll only use the training data to train the model, but we'll use the validation data to check the accuracy of the model, right? And like check how the model is performing well on the new example. So for this model, the validation data will be the new examples, right? And then on the test data, we'll check after you are satisfied with the model, we'll check at the last time that whether this model is doing great or not, right? So the test data will be used at the last time to check the model performance, right? Whether it is up to the mark for the test data as well or not. And then the deployment data. After that, we'll deploy the model, and then the deployment data basically is something that which is coming from the direct user or the direct sources, right? So let's say that if you have built the model, now if you want to use the model, so we'll kind of deploy it, and then we'll test it based on the real usage. Basically, here we want to use the model, right, into the real world, and then we want to check it. That is what the deployment data is, right? So typically the expectation is the training data is always, so again, this error on the deployment data is as high as the test data error, and the error of the test data is as high as the validation data, and the error of the validation data is as high as the train data. So basically this is the hierarchy goes on. That means In the real world, if your training data is 99% accurate, so your validation can become, let's say that 97% of the accuracy. The test data can be the 95% of the accuracy, and the deployment data can be of 90% of the accuracy, right? So no model can give you the 100% accurate, at least not now, right? So machine learning is very different, right? So you cannot expect 100% accurate on the deployment data, right? So that is how all three models are. Now we'll talk about cross validations. So what is cross validations? But before that, let's understand what is the problem with the single train validation split. So, so only using the portion of the data for training and only the portion for the validation, and like only the specific portion for the validation data. Let's consider that here, like whatever we have done till now, right? We had the data, we had split it into two part. Now this training and the test part, and now again the training data has been splitted, and it has been splitted into two part, like the train and the validation split, right? So here, consider that if your data set is very small, so your training data will be very small as well, and it will be very small the validation data, right? So consider that if your the training data is very small, right? So the things are, maybe the data is you have used into the training data for the model training, right? Those, some of those examples is not there into the validation data, or some of the data which is there on the validation data is not available on the training data, and for that reason we'll get the error, right? So if you have the small data set, so this problem is very often. That means you can, like sometimes you can get lucky, and then you can get let's say that 95% accuracy on both training and the validation data, right? But that is kind of, but that will not happen on the test data as well and on the deployment data as well. This is the problem with the single train test split, right? So what happens during the cross validation is, so cross validation will help you to solve the situations, right? So basically here you can see that, consider that we have this entire training and the validation data, right? So in the cross validation, let's say that if you are saying that fourfold cross validation, so in the fourfold cross validation, we'll divide the data into the four equal part, or you can see in this way, right? You will copy the data into the four equal part, right? So now, earlier we had this data, but now we have the four copy of the data, and every time your validation data will be changed, right? So here, so at the first time our validation data is the example number 4 and 7, and these are the training data. And the second time when you train the model, because now we have the four copy of the data, so in the first copy these would be the validation data, in the second copy these two would be the validation data, in the third copy these would be the validation data, in the fourth copy these would be the validation data. So every time the validation data will be changed, and now we have the four different model trained on the different training data and the different validation data, right? So this is how a fourfold cross validation will do. So what essentially we are trying to do over here is, here we want to make sure that we want to use every examples in the training data and every example in the validation data, right? But again, every time when you train the model, right, so essentially the training and the validation data will be different, right? And now we have the four different model, right? So each fold gives the score. We usually average our k results, right? So here, let's say that if you want to know the model accuracy, so what we do is we'll take the average of the accuracy of all the models. That is what we do, right? Which is like the average of the error, or the average of the accuracy is the mean accuracy or the mean error, right? And which is kind of very much understandable, right? So now we can show that now, like, so basically instead of taking decision based on just one split, now we'll take decision based on the four split, right? So that is what happens when we do the cross validations, right? Now you can implement the cross validations using, so here we have to import this crossval score and the cross validate functions. We are importing from sklearn.model selection over here. Now if you use the crossval score, how do we use it? So we'll have the model, and I will pass our model and the training data, and when we say CV is 10, that means we want to do 10-fold cross validation. So here the CV is 4, that means we have done the 4-fold cross validation. The same way we'll do, like we'll apply the same process to 10 times, right? And then we'll take the average of 10 different model, right? And here we can check that. So this cross-val score can give you the result of the validation data. Again, remember, all this is score is given as a score of the validation data. So here we are getting the accuracy of the validation data. And again, because we have set the CV as 10, so we are using the 10-fold cross validation, and here we are using the accuracy of all the 10-fold cross validations, right? But essentially we do not choose one, we'll take the average of the accuracy. So here we can take the mean and the standard deviation. So the mean of the cross validation is 84% and the standard deviation is 9%. That means the the variations of this 84% is 9%, right? So under the hood, what happens is it creates the CV fold on the data. In each fold, it fit the model on the training portion and score on the validation portions. And then the output is the list of the validation scores in each fold. So the output will be, this will be the score of the score. So this is not the accuracy on the training data. This is the accuracy on the validation data, right? Now, how does cross validate? So what we have seen is that we have seen this cross val score function, but how does this cross validate function work? Now this is very much similar to the cross val score, but more powerful, right? So basically it can give you the training and the validation scores both, right? That's the only reason we can use the cross validate. So it will give you the both score, the training score and the validation score as well. Again, the same way we have to pass the model, the data, we say CV as 10, and then we have to set this parameter as in return train score as true. So this will also give you the train score. And here we can see that, right? So again, it also gives you something like fit time and the score time, like how much time that it has taken to kind of fit the model and check the score of the model. We can check that this is our test score and this is our train score, right? And then essentially we can take the mean of those. So the on an average, the train score is 84%, so test score is 84%, and the train score is 90%. Again, here when we say trains, this test score, basically essentially it is a validation score in our terms, right? It is our validation score. So this is how the cross validate function work, right? Again, here is another kind of explanation of the cross validation, right? So let's say that these are like, this is for the 5-fold. So when we say fold 1, in this we'll have this 5 different split, right? So when we say fold 5, it will convert our data into the 5 different portions. The one portion will be used for the validation, another portion will be used for the training, and this will happen 5 times, right? That is how the cross validate function work, right? Now, as after that, after you satisfied with the model, remember that this cross validate function does not return you the model itself, right? This will not return you the model. This will just return you that the first time that model you have trained, the accuracy on the validation data was this, the accuracy on the trained data was this. This will not give you the model itself, right? So these technique will be used to kind of select the best model or tune the best model, right? After you tune the best model, after that, now you want to test it on the tested data. That is how we use it in the machine learning, right? So how do we do that? Again, here we have the data X and the Y. First we split into the training and testing. Now we have this model now. Now here we are using the cross validate function. When we here we're saying CVS 10. Here we are only using the training portion of the data. This is the training portion of the data. Now to take the mean standard crossval score, we have created this function which will return the mean of the training score and the standard deviation of the training score, right? And here we are using the functions, and then the result we are getting as. So the mean of the test score is 78% and the mean of the train score is 99%. So the question is, how do we know whether this test score is reasonable? How do we know whether this test score is quite enough to use this model? Now, to understand that concept, we'll understand first what is underfitting, overfitting, and the fundamental trade-off, right? So now, now we'll see how many type of error we have. So we have the four type of error. Before we understand this underfitting, overfitting, and fundamental trade-off, first we understand how many type of error. We have the four type of error. First is the error on the training data, the error on the validation data, error on the test data, and the best possible error, right? So when you have the error on the, like, this ER is the training error or error from the cross validation, we can check, right? E-validate is the validation error, which is the mean, and the validation error from the, we can get this error from the cross validation function, we can get this error from the validation score, like from the cross validate function, and then we can check the model on the test data, right? We'll see that. But how do we choose the best model? Like here the question was, can we use this same model where the test score is 78% and the train score is 99%? What is the best possible gap we can get, right? Or what is the best minimum gap that we can get between the training score and the test score? Currently, we do not know. For that, we have to understand about the training error. Like for that, we have to understand about the underfitting and the overfitting. So what is underfitting model? So let's say that here we have built the model. Here we have built a model with the very simple model, right? And then we are checking the cross validations, right, with the CVS10. So how much error we are getting? On an average, the error on the training data is 18% and error on the validation data is 21%. So here the question is, can we use the model with the error on the training data is 80%, is 18%? That means your model is only accurate as, I guess, 82%, right, on the training data. Can we use this model? Actually not. We want to have the model with the training error at least 5%, or like with the, like here we are checking in terms of error, but consider that, right? We do not want to use the model with the where it is not performing well on the training data only, right? Here we have used this model and the training error is 18%, so it is not doing great on the training data only, right? So how we can expect that this model will work good on the validation data? If this model is not even performing good on the training data, how we can make sure that it will perform well on that validation data? So this type of model is called underfitted model, right? Where the training error and the validation error both are high, is called the underfitted model. Or in another way, you can flip it around and then you can say that where the training score and the validation score both are low. In terms of accuracy, we'll check the, it is a low, right? So those are the underfitted models where the gap, like where this error are high in both situations, in both type of data. Now let's talk about the underfitted model. So here we have built this model. Now we can check that the training error is 0% and the validation error is 22%. Now in this situation, our training error is very low, it's zero. That means what? That means our model is very well understanding our training data, but it is performing poor to understand the validation data. So the gap between training error and the validation error is very high over here. If this situation comes, so here we can see that it's an overfitting situations where a model has understood the training data so well that it is not understanding the validation data, right? So that means your model is doing so perfect on the training data. So to make, now earlier we have discussed that to make a model perfect, right? Now here we were discussing as overfitted model is very complex, right? It has become so complex that it only understands the training data. It does not understand the validation data, right? We do not want the overfitted model, and we also do not want the underfitted model. We want a model in between where it is very low error on the training data and the validation data both, right? So those could be our generalized model. Now, here, what we are essentially doing is we have just splitted the data, but now here we are trying a different model. So how we are building a different model over here? So again here we are using a different maximum depth every time on the decision tree, right? So here this is our decision tree classifier we are using. Every time, the first time the depth was 1, second time the depth was 2, then the depth was 3, then the 4, then the 5, then the 6, right? Every time the depth value we are increasing. So every time when this loop will increase, right, our model will become more complex. So we are building a model from very shallow models to very complex models, right? And how many of model we are building over here? We are building total 16 model after those, right? So not 16, it's a 15 model because 16 will not include, right? So here we are building total 15 models. And every model, we are passing every model to the cross validate. That means for every model, we are doing the cross validations, right? So essentially, we want to check that how each model is performing well on both training and the validation data, right? And then we are checking the, like here we are storing the depth value and the accuracy and the score, like everything. And after that, all the data has been stored into the like into this result dictionary, and here we are trying to print the mean train this mean of the train error and the mean of the cross validation error. Here we can see that mean of the train error has gone decreasing, so the error has become decreasing, right, after we increase the depth value. But here we can see that the cross validation is stuck at somewhere, right? So we cannot do better than this on the cross validations, right? So we have to choose a model where the accuracy is both like where the kind of error is low on both training and the validation error. Or you can essentially also see in this way, that we can choose the model where the validation error is very low, right? So here we'll not take decision based on the training error, but we'll take decision based on the validation error, right? So what is the fundamental trade-off of the supervised machine learning? So this is what the fundamental trade-off is. As we increase the model complexity, that means the error on the training data will go down, right? And the difference between error on the validation data and the training data will go up, right? That is what the fundamental trade-off is. Like over here, we can see that with the increase of depth parameter, the model complexity is being increasing, right? And so the error is being decreasing, but the difference between error in the training data and the validation data is keep increasing after some point, right? So we want to choose a model where both differences is very low, or essentially you can also choose this way. You can choose a model where the validation data is very low, where it is performing good on the unseen data. So validation data is nothing but a unseen data, right? Now, let's understand what is bias and the variance trade-off. So this fundamental trade-off is also called, like this fundamental trade-off is also called bias variance trade-off in supervised machine learning. But again, there are different definition for the bias and the variance is. So what is bias? So bias is something like tendency to consistently learn the same wrong thing. That means your model will not perform good on training and the validation data both. That will be, so then we can say that your model is biased towards the similar examples, and this will lead to the underfitting. So what is variance? How do we explain variance? Variance is like tendency to learn the random things irrespective to the real signal. Where, so this means that when you have the training data, right? So in the training data will have this lot of randomness. So your model will learn those randomness it will learn the real pattern and those randomness. So essentially it will be the very less training error, but because it has learned the randomness, so it will kind of not justify the validation data. So here the error on the training data will be high, but the error on the validation data will be low. That is what the variance is, right? So essentially you understand that the model which is performing, or like if the model is underperforming, that is a bias, or like yes, and if the model is overperforming, that is the variance. You can also understand in this term, right? So how to pick the best model? So basically we have to choose the sweet spot. Again, I have already said, consider that this is a graph of the model complexity. Here we have this underfitted model where the accuracy for both training and the validation data is low. And here we have the overfitted model where the accuracy on the training data is high. Like over C, this is a signal of the training error, like this training accuracy, and this is a signal of the validation accuracy, right? So the graph will look similar to this, where if the model complexity will increase, the training error will, or the training accuracy will keeps increasing, but so as this validation accuracy will also increase, but after some point this validation accuracy will started decreasing. So we have to find that point where the accuracy is very high on the validation data. That is what, like that is how we should pick the model is, right? Now, so here we have created this function called cross validate standard deviation, which will kind of you do the cross validations and take the mean of the test and the train score, right? So here this is our this is our this entire result DFEs with a different depth parameter. With so this is the with the depth one, our mean training error is 70% and the cross validation error is 21%. With the depth 3, our training error is 14% and the cross validation error is 20%. With the depth 5, our training error is 8% and the cross validation is 19%. With the depth 7, our training error is 4%. But again, you can see that here our cross validation has been increased. So we have to find a model where the accuracy, or like here we are seeing in terms of error, we have to find a model where the error is very low. So essentially we can choose this model where the error was low, which was 19%. So we can choose a model with the depth 5. We can choose a model with the depth parameter 5 where the cross validation error is very low, right? And then after that we'll retrain the again model with the depth 5 with the entire data set, right? Not the test data set, but here we'll use this entire training data set. That is how we'll do. So what we're doing is, this is the code we have written just to check the best possible maximum depth value, as we have already seen visually, right? So this is the code we have written, right? So the minimum error that we can get is 19% at the max depth of 5. So after we find this model we can try, so we can try the model with the max depth 5. So now we'll retrain the model. So here we are reinitializing our model, this decision tree classifier with the max depth 5. Then again we are fitting the model with the entire training data. Now we'll not use any cross validation, no validation data. So we'll retrain the model with the entire training data, and then we'll check the score on the test data. Now here we can see that our score on the validation data was 19%, and our score on the test data with the retrained model with the max depth 5 is still the 90%. Now, now our model is giving 90% error on the test data, and how much error we can say? We can say that it's a 8% on the training data. Still the difference between training error and the test error is high, but there's not much we can do, right? We cannot do a lot about that, but here now we can be sure that if we deploy this model, there will be a 20% error, or approximately 20% error. That means we can hope that this model will always be 80% accurate model. This is what our hope is, right? And now we can use this model into the while, and then we can show that if we'll use this model, now we can trust this model for 80% of the time, right? So if like this model can fail for 20% of the time, right? We can say this way, right? And we can be very much confident about that because this is how the model we have tested, right? So what is the golden rule? The golden rule is like, even though we care about the test error, right? But the test data cannot influence the training phases in any way, right? And we have not done that way, right? We have only used the validation data to check to find the best model, and then we have retrained the model, and then we have used on the test data. So basically we have to be very much careful to not to violate this rule. That means do not show your data, do not show the training data, the test data to the model, right? And even lots of even like expert have kind of made this mistake, right? So they have kind of shown their test data to the training to the model, and then they have achieved the higher accuracy, but that was not the correct model, right? That was not the correct way. So we have to be kind of very much sure not to break this rule. So how do we avoid these golden how do we avoid this violating golden rule? It's a simple tricks. First, we have to split the data into the two-part training and the testing, and do not look at the test data ever. As a human also, we do not have to right to look at the test data. Whatever we have to do, just split the training data again into two part, into like validation or the training data, or you can use the cross validation technique, right? And then you can train your model on that, find the best model, retrain the model on the trained data, and then test on the test data. That is the one way we can do to avoid the kind of violating the rules, right? And yeah, that's it. So here is a summary. What we have discussed, we have discussed about what is the importance of generalized model, how do we achieve the generalized model, what is the training data, what is the test data, what is validation data, what is deployment data. We have discussed all this. We have discussed about the cross validation functions, right? We have seen the typical steps which involves in the supervised machine learning problem. Like we train the model on the training split, we'll fine tune the hyperparameter or choose the best model hyperparameter on the validation using validation data, and then we'll retrain the model on the best data on the best hyperparameter, and then we check the performance on the test data, right? We have discussed about the overfitting, underfitting, fundamental trade-off. So we have discussed a lot in this lectures, right? So what next we'll see, so next we'll talk about KNN and the SVM model. So both are the different models. We'll talk about pre-processing technique, which includes like imputation, scaling, one-hot encoding, and what is SQL pipeline. So in the next lecture, we'll have a lot of things to discuss, right? But for now, thank you very much.